Welcome once again. Today we are going to discuss about electric charges and electric field in a vector form. Okay, so let's say we are having our charge here, our positive charge here, and we are also having our point charge. The point charge is usually represented with a positive charge, or the point charge is always what? A positive charge. And let's say we are having another positive charge here. Okay, so if you are asked to find the electric field between this point and the charge, then we can find the distance between them using Pythagoras theorem, because here we have been given the points in the Cartesian form, okay, which is the 3 and 4 coordinates. So using Pythagoras theorem, then this distance will give you 5 meters. Okay, so from our formula, which is electric field is equal to KQ all over R square, then this will be the normal calculation. This is the K, which is the constant, and this is the charge. The micro stands for 10 raised to the power negative 6 divided by what? Your 5 square, or your 5 meter square. So from here, this is what we are going to get for the electric field, but this is only the magnitude. So for us to find the vector form of it, we have to find the unit vector, or there's another method that we can use by finding the direction. Here we can find the direction or the angle between it. Okay, so from here we can find the angle. We are having our opposite and we are having our adjacent. So the normal trigonometry ratio supposed to be used is what? Tan. So our theta will be equal to tan inverse of what? 4 over 3, giving us 53 degrees. Okay, so if you are having our 53 degrees here, then if you are finding the s component of our electric field, the s component usually what correspond with what? The cos or the cosine trigonometry, and our y components usually correspond with the what? With the sine trigonometry. So if you want to find the s component of the electric field, you just multiply your magnitude by what? By the direction, which is the cos 53. Okay, and if you want to find the y component of the electric field too, you just multiply by sine 53, giving us the y component in the form I and j. Okay, so this is actually another way of what, or this is the local way of finding the vector form of an electric field. But let's consider another alternative here. Okay, so as you can even see from here, from the sticky notes, our unit vector is equal to what? The vector itself. Vector is given by the magnitude times the direction. So our unit vector is equal to the vector divided by the magnitude. So from here, our magnitude and our magnitude will cancel, giving you what? Only direction. So for unit vector is actually having a magnitude of 1, and its main function is to determine the direction of a vector. Okay, so now let's consider this one as an example, or let's consider this alternative method. After finding your magnitude of the electric field, you just multiply it by what? Your unit vector. But how are you going to get your unit vector? From here you are having your vector to what? 3i plus 4j. After calculating your magnitude, which is the r, from a Pythagoras theorem, your magnitude is what? 5. So just divide your vector divided by the magnitude. You are going to get 0.6i times 0.8j. Okay, then from there, this is your magnitude. This is the magnitude of the electric field. Multiply it by the vector. You are going to get the same value as what obtained from here. Okay, so there are two alternatives that you can go about. Let's consider this question for example. This question is, calculate the electric field of what? Of a 40 millicoulomb charge in a centimeter Cartesian plane at the points 6 and 2. So this means that what? If it is 6, it is 6 centimeters. If it is 2 centimeters. Assuming the charge is located at the point -4 in the plane. So here you are asking to find the vector form of the electric field. So this is actually the diagram, or the free body diagram, that you can draw to enable your assumptions, or it can enable your understanding of what solving the question. So from here, as you can all see, this is your 6 and 2. This is the point, and this is the charge. Okay, so the distance between them, you can calculate it by what? If you calculate it, it will give you what? 10 centimeters, and from here it's going to give you 6 centimeters. So using Pythagoras theorem again, you can use to find out the distance of separation, which is going to give you 11.66. Okay, by converting it into meters, it will give you 11.66 times 10 raised to the power -2 meters. Okay, so now let's move to the real solution of it. All right, so from here you are giving what the charge, you are giving the charge to what 4 millicoulombs, and the milli stands for -3 coulombs. Okay, and our key, we all know our key. So when you are finding for the electric field, you, after finding your magnitude, this is what you are going to get for the magnitude of the electric field. Then from there you are going to find what your unit vector. So from here, your 10I plus 6j divided by the magnitude, which is going to give you 0.85I plus 0.81j. Okay, so then your E is equal to your E vector, or the electric field vector, is equal to what? The magnitude times the vector, which is going to give you in a form of what? Your I and j components. And the unit for it, don't forget the unit. The unit is what? Newtons per coulomb. Okay, so now let's move to another concept of what? The electric field. So here, let's talk about the summary of electric field and dipoles. Okay, so let's consider an electric field. If you are having a charge particle here, we are having another charge, they are dipoles. Okay, let's say they are all having the same magnitude. Let's assume that they are all having the same magnitude of charge. Okay, and here is negative and here is positive. When you project an electron, you can all remember from our previous lesson about projectile motion. The moment you project something, it undergoes a parabola form. So let's say we are having what? An electron. The moment you project an electron through this electric field, because an electron is what? It's a negatively charged particle, the negative what field is going to what? To repel it to the positive, and the positive is going to attract it according to the laws of what charges. Like charges repel, and unlike charges what? Attract. So here, when we are asked to find the acceleration of the electron, we can just find it from here, that to find the acceleration of the electron, our E is equal to what? From our E, which is the electric field, is equal to force divided by charge. We can make force the subject. Our force is equal to what? The charge times the electric field. But since an electron is negatively charged, our Q will be what? Our Q will be negative. That's why our F will no longer be what? Q times E, but it's equal to what? Negative Q times E. Then you can all remember that from kinematics, from Newton's second law, our F is equal to what? Ma. Okay, so then these forces are the same. Then our Ma is equal to what? Negative Q times E. We make acceleration the subject. Acceleration will equal to what? Negative Q E divided by the mass. Okay, so to calculate for the velocity of the electron, since we are all having our acceleration, after calculating for the acceleration, or the value that you get for the acceleration, then that's it. So supposing that the electron was initially at 0, then this is going to be our velocity of the electron after projection, or after trajectory. So our v is equal to what? The square root of what? 2as. Your a is the acceleration, your s is the distance. So to make it more straightforward, you can just substitute the value of a into this formula. Then, but note that this formula is actually what? Based on one dimension, or in one plane. That's when you can use it. There can be two planes where we are going to have our x and y. That one we have to resolve it in your y and your x component as well. So now let's move to how to calculate for the kinetic energy. Okay, when you're calculating for the kinetic energy, we know our v. This is the formula for the v. Okay, so our kinetic energy is equal to mass times velocity squared divided by 2. So our mass is here divided by 2. Then this is our velocity. So velocity squared is going to give you what? It's going to cancel the square root. Okay, giving you what? M over 2 times this one. But these two, there is a 2 at the denominator and the numerator, so they will cancel out. Likewise the m as well, or the mass. So here for the kinetic energy, the mass is not important as well. So we can just derive our kinetic energy formula from here. That our kinetic energy formula is equal to what? QE times S. From our previous lesson, QE is equal to what? Force. Force times distance, it will give you what? Work done. That's why we can say that change in kinetic energy is equal to work done. Everything applies here. Okay, so now from work done is equal to force times distance. Our force is QE, as I said earlier. our distance is s. So then our kinetic energy is equal to work done, which is equal to QE times S. Okay, so now let's consider a condition for an electron to suspend in the electric field. Using the same electric field, let's consider a situation where we want the electron to suspend in the what? In the electric field. Sorry, the wind is quiet blowing the paper away. So let's consider this one for instance. If you want something to suspend in the air, then the force that is holding it should be what? Should be directly equal to the weight for the things to suspend. And the weight here we are talking about is the what? Is the gravity. Okay, the gravity. So from our Newton's third law, which is the reactions and actions are opposite but equal, your forces. So the force that is what? That is enabling the force that is enabling this electron to be sustained or to be held in this electric field, the force is equal to QE. Okay, then our weight too is equal to mg. The m is the what? The mass of the electron. Okay, so from here we equate these two forces. So our Fe is equal to Fg, then our QE is equal to what? Mg. So if you are given an electric field and a charge, okay, so to determine the mass in which the electron should gain in order to suspend in the electric field, then you have to use this formula to find the mass of it. So I'm having several questions that I'll be posting that will make you understand it better. So after that, I'll be posting it, you try it, and you get a better understanding of it. So let's consider another condition here. So let's consider a condition for what? Our electric field to be equal to 0. There are two main conditions that we can consider for our electric field to be equal to 0. The one is what? When the two charges, when there's a dipole. Dipole means they are having the same charge but what? Opposite. They are having the same magnitude of charge but opposite signs, is the positive and the negative. Okay, so let's say for here, this is the direction of the electric field, and as you can all see, electric field, it moves from the positive to the negative. So if we are having the electric field direction to be this way, then means that here is positive and here is what? Negative. Here is negative. So here too is what? Positive. That's a mistake I made. So here too will be what? Here too will be positive and here will be negative. Okay, so this means that what? We can make an assumption here that since there is a dipole here and we are having our F, if here is negative, then this positive charge will be what? Attracted to the negative side of the field. This negative side will also be attracted to the positive side of the field. And since they are having the same magnitude, the forces will be the same. But if the forces will be the same but in opposite direction, then our force will be equal to 0. Electric field is equal to what? The force divided by the Q. So if our force is 0, then definitely our electric field will also be equal to what? 0 as well. So all what I'm saying is this one. Okay, so the force net, okay, the force net or the net force will be equal to what? 0. Since they will be all having the same magnitude by opposite direction, it will give you 0. Okay, now let's consider the second condition where our net force will be equal to 0, or our net electric field will be equal to 0. Let's consider a charged circular ring. Okay, let's consider a charged circular ring like this form. If you're having this charged circular ring, imagine that everything is charged positively. As we can all know that electric fields, especially the positive, the electric fields moves away from the charge. Okay, so let's say every point on the circular ring is what? Positively charged. Then this is how the electric field will be what? It has also been uniformly what? Positively charged. It's not uneven, it has been uniformly. So the charge at every point are equal. So this means that the electric field will also be what? The electric field will also be equal. And this is the center of the what? So this means that all the electric fields will be pointing to this direction. All the electric field will be pointing to the center. Okay, so if E1 and E2 are of the same magnitude but they are opposite direction, it will give you 0. This one too and this one too, they are all meeting to give you 0. Supposing there's a positive charge and a positive charge here, everything will meet at the center and it will give you 0. So for that matter, there's another condition where our electric field will also give you 0. Okay, so this is it. So since our r is the same at every point, and the radius too is the same. Okay, the radius is the same at every point from the center. For that matter, the electric fields are opposite but equal. Hence, everything will be zero. But let's consider this special case. For this special case, for instance, our electric field it won't give us zero. Okay, this one is a what? It's a semicircular or a semicircle. Okay, it has been divided into two. Let's say we are considering this circular. We have divided it into two, and it is positively charged. So this is what all the electric field will be pointing what towards the center. Okay, but here there is no other ring to also oppose it in order to make it zero. So this is what if this electric field is moving here to the center, this is actually the direction of it. Okay, this will be the direction. Here the E1, this will be the direction when you get to the center. So if you are finding for the net electric field, then we can resolve it this way. From our vector forms, if we are having E1 and E2, we can find the resultant from here. So this will be the resultant, and the resultant will face directly in the negative y-axis. Okay, it will face directly negative y-axis. So that will be the resultant. So this will be the direction of the net electric field. Okay, so now let's move to a moment of a dipole. So when we are talking about moment of a dipole, for mechanics, our moment is equal to force times distance. Okay, but in our electric charges, our moment is equal to what? Our charge times the separation. This will be the separation. This is the separation, or the dipole axis. This is the separation, and this is the charge. So the charge times the what? Times the dipole axis. Okay, but our moment, we should all keep in mind, moment is what? It's a vector quantity. But in electric charges, the direction of the moment always start from the negative to the positive. You should always keep it in mind. That's another qualitative question. It also moves from the direction of the moment moves from the negative to the positive. Okay, so let's talk about torque and moment. When I'm talking about torque and moment, let's consider the situation A and B. Okay, with the same electric field as discussed earlier. This are dipole. Okay, so this force will move it to this direction, and this force will also move to this direction. After all, the forces are the same. For that matter, your net force will be equal to zero. And if the net force is equal to zero, then there will be no rotation, because this one is moving to this direction, this one is also moving to this direction. So it will become stable. There will be no rotation, though there's a dipole axis or there's a separation between them. Now, and if the net force is zero, then our zero times the dipole, which is giving you the torque, will also give you zero, because our torque is equal to the force times the dipole axis as well. The torque is also similar to the moment. So when we are having our force here, we are having our distance here. If the force is zero, then our torque will be equal to zero. Okay, now let's consider this situation too. Here we've interchanged the position of the dipole. But so if here is a negative, and here is positive, then you should consider it in mind that there will be a repulsion. From here. It will repel the negative. This one, there will be a repulsion which will repel the positive. And these forces are also opposite, but they are the same in magnitude. For that matter, your forces will also be equal to zero. Your net force will be equal to zero times the distance will give you zero. So our torque is zero here. But now let's consider this one. For example, when the dipole is perpendicular to the field, definitely there will be a rotation. Okay, definitely there will be a rotation, because here is positive and here is negative. It will be attracting, so there will be a force that will be attracting it. Here too, there will be a force that will be attracting it to the other side, because here is positive. For that matter, there will be a rotation, and the rotation is called the torque. Okay, there will be a rotation. So as the positive charge is moving to this direction, the negative charge is also moving to this direction. Okay, so from this diagram, our torque net is equal to T1 plus T2. Okay, and our torque is equal to the force which is causing this thing to move, this force, times the L. The L means the half of the dipole axis, not the full dipole axis, the half of the dipole axis. That will give you the L. So generally our torque is equal to our torque, let's say we are finding for T1, our torque will be equal to what? F1 times what? L. Okay, where our L is what? D over 2. Now, here you are seeing that what? Hence, our T1 is equal to what? F1 times L. Our T2 is equal to what? F2 times L. But here you see they are dipole. The charges are the same. Electric field too is the same. For that matter, the force F1 and F2 will also be the what? Will also be the same. So F1 and F2 will be the same. The length will also be the same. So our length, as we stated earlier, is d over 2. So we have substituted it here, d over 2, here to d over 2. But our F1, as I stated earlier, F1 is equal to F2. So our torque net will be equal to what? F over d2 plus F over d2. When you add these two, you are going to get what? Force times what? The dipole axis, which is the same thing as the moment as I stated earlier. Okay, so now let's consider this one. For example, here the dipole is not what? Fully perpendicular or what? Fully in the what? The y-axis. Here it's actually what? It's actually diagonal. If it's diagonal, there will still be a rotation, but as it is diagonal to the electric field, there's an angle that will be formed. Okay, there's an angle that will be formed here, and this angle, this our motion diagram. So this will be the angle. The angle here is the same thing as the angle here from our alternative what? Angles. And our d is equal to what? Our L here, this is the L. Our L is what? D over 2. From the dipole axis, dividing it by 2, we are going to get what? D over 2. And this is our L. For torque, we actually depend on what? The perpendicular what? Length. So we actually focus on this length rather, not this length. Okay, so here our torque is equal to what? Moment. So if you consider this one for instance, this one is a vector, this one is also a vector. So our torque is equal to what? Moment times what? Electric field. Multiplying the what? The sine of the what? The angle. So this is another formula for what? For torque. P, which is the moment, and the E, which is the electric field, sine the angle between them. Okay, so let's talk about the derivation, how we got about it. Our torque is equal to what? Force times distance. Our force is equal to what? QE. As we all stated earlier, force is equal to what? The charge times the electric field. Now, our charge times the electric field times the distance. Okay, that will give you the torque. But our QD, as I stated earlier, QD, which is the charge times the distance, as I said earlier from here, our charge times the distance is what? Moment. So from here, our charge times the distance will give you moment. Then we can make what? From this expression, we can make Q and D stand the same because they are multiplying and it is commutative. So Q and D times E, which will give you the moment times what? The E. Hope you all get it. So from here, we can just take one of the triangle from here. You can just take one of the triangle, expand it to see what's going on. So this is the angle between it. Then from our trigonometry, sine theta is equal to what? L, which is the opposite over the what? Hypotenuse, which is 2. If you are making L the subject, our L will be equal to what? D sine theta over 2. Okay, our L will be equal to D sine theta all over 2. So then T is equal to, as we have stated earlier, that T is equal to what? Only one torque, which is T1. Let's say we are taking only one torque, for instance. Our T1 is equal to what? Force times L. So the same thing applies here. T is equal to what? Force times L. Then our T net will be equal to what? FD, because the whole of this is what? L. So FD sine theta all over 2 plus FD sine theta all over 2. When you add these two, you are going to get what? FD sine theta. Okay, this is when the thing is in what? This is when the thing is diagonal. Okay, but our torque net is equal to what? Our torque net is equal to FD sine theta. But what's our F? Our F is what? QE. So we come and substitute this F with what? QE. So now we are having QED sine theta. But what is QD? QD is what? Moment. So moment, which is this one and this one, will give you moment. Okay, so moment times the E sine theta. So this is our derivation of the formula. Okay, this is the derivation of the formula. This thing is showing what? The direction. So it makes everything here what? Vector. For that matter, our T net, if we are having our moment vector and we are having our electric field vector, you can just multiply the two and get what? Torque. So since theta shows the direction, then they are expressed in a vector form. That's all the idea about it. Okay, so now let's move on. Now let's move on to work done. Work done obtained from torque. When I'm talking about work done obtained from torque, our work done is given by what? dW is equal to T, which is the torque, times what? The d, or the change in what? The angle. Okay, where the T is equal to what? P, as we've derived earlier, our T is equal to what? P sine theta. Then our work done is equal to what? Our work done is equal to what? Negative was the integral from theta 1 to theta 2, multiplying this expression times d theta. Okay, the reason why it is negative is that the reason why the integration is negative is because you see in talking, as the thing is moving like this, let's say this is what? 90 degrees angle. As the thing is moving, the angle is decreasing from 90 degrees to, let's say, 0. By the time this charge will get to this side, then the angle has decreased from what? From 90 degrees to 0 degrees. That is why we are having a negative integral here. Okay, so the integration is negative because in torque the angle theta decreases from what? Theta 1 to theta 2. When we are having anything that is decreasing, we are getting negative. Okay, so from here our work done is equal to what? PE. We are going to exclude this one, or we are going to take this one out of it because it's a constant. So PE, negative PE, integral of what? From theta 1 to what? Theta 2 sine theta d theta. So from here, if you are doing integration from our normal integration, this is how you are going to get. If you integrate sine theta, you are going to get negative cos theta. Okay, that's from trigonometry. If you integrate sine theta, you are going to get negative cos theta. So our negative cos theta, then here is what? Our theta 1 to theta 2. Okay, so here our negative PE is equal to what? Negative what? Cos theta 2 plus. The reason why it is plus because we'll be factorizing this negative out. Okay, so if we factorize this negative out, automatically this will become what? Negative, and this will become negative, and this will become positive again. Okay, so let's move on. You understand what I'm trying to say better? So negative PE is equal to what? Negative cos theta 2 minus plus cos theta 1. Okay, so when we factor out this negative, we are going to get what? Negative PE times negative, then bracket open, cos theta 2 minus what? Cos theta 1. Negative times negative will give you what? Positive. Okay, so from here, our positive PE times what? Cos theta 2 minus cos theta 1. You can decide to multiply through by the PE in order to expand the bracket. So generally, our work done is equal to what? This one. Our work done is equal to PE cos theta 2 minus PE cos theta 1. So from our previous lesson, as we all know, work done is equal to a change in kinetic energy, or the change in what? Potential energy. Negative change in potential energy. Always keep it in mind. So where our U is what? Potential energy. So our work done, when we are considering the potential energy, for instance, our work done is equal to what? Negative change in what? Potential energy, which is U2 minus U1. In general, our U, which is the potential energy, is equal to what? Negative PE cos theta. Because of this negative here, as you can also, because of this negative here, everything here will give you what? PE cos theta. But because of this negative will be multiplying to give you what? Negative PE cos theta. Hence, our work done is equal to negative change in what? Our negative change in potential energy. So to proceed, we are going to what? Continue with what? Our electric field, which is a field of what? A field of a line of charge. Okay, so this one, it contains a whole lot. Okay, so in my next video, I'll be explaining it bit by bit in order to arrive at what? Something like this. Okay, they are all about electric field. So in my next video, I'll be explaining everything bit by bit in order to what? Get to this point. So if you know that this video has been very, very important to you, make sure to subscribe and like it. And if there's anything you don't understand too, feel free to also make it in the comment section. I will see it and what? Do more video in order to boost your understanding. Okay, so don't forget to subscribe if you've not subscribed, and also like it as well. If there's any problem or challenge, give it out in my comment section. I'll make sure I'll do everything about it in order to understand it well. Okay, have a great moment.